Hello guys, welcome back to Medzone African Motives. Still on our power machines N5 revisions, working this time on compressors. We shall be focusing on the question paper which was written in November 2022 exams. If we are dealing with compressors, what you need to simply understand is that these are an application of whatever that we talked about when you're dealing with gases, or when you're talking about thermodynamics of gases, meaning to say all that part that we're dealing with before is just an application, a continuation. So all you just need is to know your type of compressors, the one that you're working with, and so forth. All right, so here we are given a single acting, a single cylinder reciprocating compressor runs at 120 revs per minute. So we're given the speed where the speed of the compressor in this case, which is given as 120 revs per minute. The volumetric efficiency is 76%. So we are given in this case the volumetric efficiency, which is given as 76%. The diameter is 2 times the stroke length. So the diameter is equal to 2 times the stroke length. Then the air used is 12 cubic meters per minute. This is volume, cubic meters. This is the unit of volume. So we are told that the air that is being taken, which is if you're given volume per minute or volume per second, that is your effective volume in this case. So we are given the effective volume of 12 cubic meters per minute, all right, which is going to work together with the speed in revs per minute. And at a pressure, take note, this is the air used, and it's at a pressure of, so we're given the inlet pressure, which is P1 of 104 kilopascal, and a temperature of 28 degrees Celsius. That is the initial temperature there, which becomes 28 plus 273. We are supposed to convert to kelvins in this case. So this is going to give us 301 Kelvin. All right, the air is delivered at, to deliver, this is at the output. So we are talking about the at the output conditions P2 and T2. So here we are given is delivered at this pressure, kilopascals. This is the pressure. So that's we are given P2 in this case. All right, so that's our P2 is 850 kilopascal. According to the law, which is PV to the exponent of 1,3 is equal to a constant C, whereby we are given the index of compression from there, which is our N. Remember, it's supposed to be PV to the exponent of N is equal to C. So they are directly giving us the value of N. Say our N is equal to 1,3, which is the index of compression. Then the clearance volume is negligible. So meaning to say there is no clearance in this case. We're dealing with a condition where there is no clearance. And also we're given the gas constant, R in this case, which is 0.288 kilojoules per kg Kelvin, per kg Kelvin. That's why our temperature is supposed to be in Kelvin, because this is taken in per kg Kelvin in this case. All right, so, and take note, we are given this is a single acting single cylinder in this case, which does not affect our calculation on the speed when it is a single acting. It affects when it is a double acting. It affects your speed. Your speed is going to be 2n. So here it is just going to be 1 times n for a single acting. So it does not affect us that much. But what is important is that we do not have the clearance in this case. So in terms of the sketch that we're supposed to have, we're simply going to have something of this nature. Remember, the ratio that's going to happen between the pressure and the volume in this case. So we're supposed to have something like this, since we do not have the clearance taken at these conditions. All right, so remember, we have got our pressure. So this is the first point, the second point. So this was going to be our P1, our P2. Here we have got volume. So this is pressure here. This is volume. So that's our V1 and our V2. That's what that was supposed to be the condition, taking the law of PV to the exponent of N is equal to C. So that was a condition when there is no clearance. All right. Okay, the question here is to calculate the stroke volume in cubic meters and the diameter in meters. So you're supposed to calculate two things here, the stroke volume and also the diameter. All right. If we are to consider here, like I said, this is an application that you just need to know your formulas and so forth. All right. So if we are to check, we have a formula. From our formula sheet here, we can consider working with the volumetric efficiency and also the effective volume to calculate the stroke volume, which is Vs. We have got so many formulas that we can consider, but we are supposed to take appropriately the formula that corresponds to the part that we are supposed to work with in this case. Okay, if we check here about the efficiency, it follows that the volumetric efficiency in this case, which can be from the volumetric efficiency, is given as the effective volume over the swept volume in this case, which is the stroke volume that we are supposed to calculate times 100%, or we can take it from this formula. But as you can see from here, we've got a lot of things to consider. We've got to consider P2, P1, but we can also use this formula. It still gives us one and the same thing. All right. So in this case, the best formula to use was this one. We do not have a lot of things. So these two, they are equal. We can use this, or we can use this, or we can use this, but this one, we do not have relevant information. So we are going to apply this one. This one is the easier part because we have the effective volume. We just need to calculate the stroke volume in this case. So that was the formula that we are going to apply in this case. So meaning to say, from this formula, we saw that, let me write my formula here. We saw that the volumetric efficiency is going to be equal to VE over VS times 100%, which is for the efficiency, okay, which we are talking about our effective volume. So let us substitute our values. Our volumetric efficiency, that's 76%. If we divide by 100, this one, it will be 0.76. So we are just going to write it as 0.76 is equal to, take note on the effective volume here. Our effective volume is given as cubic meters per minute. So let me write this is 12 cubic meters per minute so that we do not have confusion at the end. So we are supposed to calculate this Vs, which is our stroke volume in this case. All right. The 100% is the one that I divided here so that it gives us a decimal 0.76. So if you are to take note on your calculations here, you are going to obtain the stroke volume in cubic meters per minute also, because what we are given as the effective volume is in cubic meters per minute. All right, let us formulate this and calculate our Vs. So we're going to cross multiply. So we're going to have 0.75 Vs is equal to 12 cubic meters per minute in this case. Okay, if we divide by 0.75, that means we are going to have 12 over 0.76. Where am I getting the 5 here? This is a 6, all right? So that's a 6 here. So you're going to divide by 0.76. You are going to obtain 15.789, which is in cubic meters per minute. Because you are using, in actual sense, you are not even supposed to write here that this is cubic. You are supposed to know, because already we took this value in what? In cubic meters per minute. That's what I'm trying to say there. So this is cubic meters per minute, meaning to also say on your final answer, you shall obtain it in cubic meters per minute. But that's not what they want. They need this answer in cubic meters. This answer is supposed to be in cubic meters. So what are we supposed to do now to remove per minute? We are going to apply the speed. That's where you use the speed now in order to obtain this equivalent 120 revs per minute. So remember, revs per minute, we are simply talking about this. N is 120 revs per minute. This means 120 revolutions per minute. So this one that we have here, in order for us to cancel per minute that we have here, it simply means our VS is 15.789 cubic meters per minute, means over a minute. So in order for us to cancel the minute, we must have our ref per minute with a minute on top, so that the minute and minute will cancel. We remain with what? Cubic meters per revolution. That is, these are cubic meters direct when it's like that. All right, so meaning to say, in order for us to have that, we are going to multiply this by a minute over 120 revolutions. Okay, so this can cancel now, meaning to say our answer is going to be taken as VS, which is 15.76 times. We are going to multiply this. We divide by 120 because here we've got this value here divided to 120. So if we divide to 120, if we multiply by 1 over 120, we are going to obtain 0.13157 and so on, which is 132 in cubic meters per a revolution, meaning to say per each cycle. So it means this is just a direct volume that you're going to take in cubic meters. All right, so in actual sense, what are we actually saying here? Given the volume, in this case, given our VS in cubic meters per minute, for us to convert this VS to cubic meters, we are going to multiply the volume that is in cubic meters per minute times 1 over n, whereby n is in revs per minute, whereby n is given in revs per minute. So you multiply by 1 over n. This is the formula that you're going to have. If it is a double acting now, when you are dealing with a double acting, this will be 2n. You're going to multiply by 2n. That is the whole idea there. All right. So I think with this short formula, that means we can summarize this with this way. On this question, we're supposed to simply say from our VS here at this part that we got in cubic meters per minute, because we've got our volume in cubic meters per minute. All right. If it is in cubic, if you are given, they might give you in cubic meters per second, meaning to say you are supposed to multiply by 1 over n, whereby n is in revs per second. If you are given rev per minute, your n is supposed to be in revs per minute. All right. So here we have got cubic meters per minute. So meaning to say our VS from the value in cubic meters per minute, it was simply going to be 15.789 times 1 over n, which is the speed in revs per minute, and our speed in revs per minute was 120. So it's going to be 1 over 120. So that gives us our VS at the end, our answer in cubic meters. All right. So meaning to say we are going to obtain the same answer, 0.132 in cubic meters from this formula. All right. So I hope you can take it in a way that you understand. If you understand the principle of conversion of units from this, then you can simply apply the same technique. That's the idea there. All right. So if we check on the other part, it was to calculate this stroke volume and also to calculate the diameter, in this case in meters. So we're given to calculate the diameter in meters. Remember, from our stroke volume, we understand that it was taken from this formula for the diameter. Let us just calculate our diameter here. From our stroke volume, we understand that it was taken from area, which is the bore area times what times the stroke length. The area being taken from pi d squared over 4 times the stroke length. So that is the volume, area times the stroke length. So we are given, in this case, we have the stroke volume. Between these, we've got a relationship between the diameter and the length that we are given. Remember, they told us that the diameter is 2 times the length, meaning to say from this part of the diameter, we can play around it to formulate or to find an expression, an equation that is only in terms of the diameter, because we want to calculate the diameter. So here we are supposed to remove this L and write it in terms of the diameter. So from this, we can divide by 2, meaning to say our L is equivalent to D over 2. So where we have got this L, we are going to substitute D over 2. So that means we are going to have our formula at the end as Vs is equivalent to pi d squared over 4 multiplied to the L, which is given as d over 2. So that is going to be d over 2, not d squared, but d over 2 like this. So that is what you're going to have. So we can calculate the time because we've got this as the only unknown value. So let us substitute our values and see what you're going to have. Remember, our stroke volume is given as 0.132 cubic meters, which is equal to, so here we can multiply on top, everything on top here. We can multiply this part on top. So that is going to be pi times d squared times d, which is going to be d cubed in this case, over, you multiply the numbers in the denominator together. That is 4 times 2, which is going to give us 8. So that's it. We can find the value of d. As you can see, we've got only one unknown. So you can cross multiply, then divide by pi, or you can simply multiply by 8 over pi, both sides, by 8 over pi, both sides, all right? Or you can do the cross multiplication as we are used to that. That is going to be 1 times pi d squared, which is pi d cubed, sorry, which is pi d cubed is equal to 8 times this value. So that is 8 times 0.132. So as I'm saying, you're going to divide by pi. You're going to divide by pi both sides. So in order for you to obtain the value of d in this case, we are going to have our d cubed equal to this expression that we see. So instead of having this expression again on your calculator, just find the value of d by introducing the cube root both sides. In this case, we're going to introduce the cube root. Since there is a 3 here, you introduce the cube root. So meaning to say d is going to be the cube root of this whole value that we see. So that was going to give us 0.695 meters at the end. All right, so that is our diameter in meters. Sometimes they might ask you to express this diameter in millimeters. You multiply by 1,000. In this case, it was in meters. So that is it. That is how you're supposed to answer the first question. Calculate the stroke volume. From there, you move on to the diameter. All right, let's check the other part of the question now. They want us to calculate the delivery temperature in this case, which is the delivery temperature, that's T2. At the delivery, we've got P2. We are also to have T2. So like I said, the application of compressors is the same as what we used to work with when we're dealing with gases. So if we are to check here, there is a relationship that you can consider from the pressure, because we've got pressure, P1 and P2 in this case. If you check from your formula sheet, these are direct applications of gases, okay? So if you come here, we are going to see that we can relate our temperature to pressure. We can also relate our temperature to the volume. Since we are not given these volumes here in this case, meaning to say we are going to use this part of the formula, all right? Meaning to say T2 over T1 is equal to P2 over P1 to the exponent of n minus. We have everything here and we want to find T2. So that means we are going to use that formula. As we can see here, we've got everything. So just for the sake of the formula here, let me write my answer here so that you can see our information here. All right, so that means 4.22. We saw that from that formula, we're given that T2 over T1 is equal to P2 over P1 to the exponent of n minus 1 over n. Like I said, we're going to use pressure because we've got pressure in this case. These pressures, we have them. So to find T2, we can even remove this T1 by multiplying by T1 here. So we're going to multiply by T1 here. So this is going to cancel. So meaning to say we're going to have our T2 is equal to T1 into P2 over P1 to the exponent of n minus 1 over n. So we can just substitute our values. T1, that is our temperature in Kelvin, which is 301, into P2, which is 850. In pressure is supposed to be in kilopascals, all right? Then over P1, which is 104, everything to the exponent of n minus 1. So this is n, which is 1,3 minus 1 over N in this case, which is 1,3. Guys, this whole part, it's you and your calculator. Simplify everything from your calculator. That's we are going to obtain 488,784 Kelvin in this case. Okay, this is 784 Kelvin. All right, so that is how we're supposed to calculate the delivery temperature, which is the temperature at the output. That is our delivery temperature, that is T2 in this case. So compressors, guys, direct application of gases. So you need to know even the second part here, to calculate the power. In this case, the power required to drive the reciprocating compressor. All right, so if we check again the power, since we are given our volumetric, our effective volume in this case in cubic meters per minute, meaning to say we can use it, because remember, work done when given in terms of kilojoules per second, it means it is equivalent to a kilowatt. So we are going to use the formula for work done, having P1 VE in this case, which is our effective volume. But in order for us to have kilojoules per second, we are supposed to use this in cubic meters per second. All right, so that is, or you can simply take this formula, but as you can see, this whole part here of MRT1 is the same as P1 VE. This is one and the same thing. So meaning to say, you can use even this formula on this side here, this one, you still obtain the same thing. All right, so in this case, I'm just going to relate to the first one, but here take note that your effective volume is supposed to be in cubic meters per second, so that we obtain kilojoule per second, which is equal to what? Which is equal to kilowatt. All right, so let us have our formula into consideration. All right, let's see here. So remember, our formula, it was given in terms of work done, but here we shall write it as the power, because we are calculating the power in this case. All right, so that's 4.23. So our power is going to be given, we saw our formula was P1, which is the pressure at the input, times the effective volume, which I say this must be in cubic meters per second. All right, so this is into N over N minus 1. You're just taking that formula as it is. All right, which is into P2 divided by P1 to the exponent of N minus 1 over N, like this, minus 1. All right, so this is the formula that we are going to use to calculate the power. In this case, P1, we have got the pressure in kilopascal. This is our pressure here in kilopascal, which is 101. So that is going to be 101 in kilopascal. So meaning to say our answer, that's why it is supposed to be in kilojoule per second, because we are using this in kilo values. All right, then the effective volume in cubic meters per second. Here we are given this in cubic meters per minute. So we're going to divide by 60 to remove per minute into per second. So it's 12 over 60 in this case. All right, so this is going to be times 12 over 60 times N. Remember, our N is 1,3. So our index of compression, so it's going to be 1,3 over N minus 1, which is 1,3 minus 1. All right, into P2 over P1. These are the pressures again in kilopascal. Remember, P2 here was 850. P1 is 104. So it's going to be 850. 850 for P2 over 104. Where am I obtaining 100 here? This is 104, and P1, this is 104. Sorry for that, guys. So this is 104. All right, to the exponent of N minus 1. Remember, our N is 1,3, so it's going to be 1,3 minus 1 over 1,3. All right, so this whole part, we just subtract a 1. As it is. So this is direct application. If you're dealing with compressors, direct application of gases. This, we talked about this when we're dealing with thermodynamics of gases. So meaning to say we still have the same thing. So the power was going to give us 56,231, which is in kilojoules per second. And this simply means we are talking about the kilowatt in this case. So that's 56.213 in kilowatts. All right, so that is how we are given these questions. That is how our questions are given as when we are dealing with air compressors, dealing with a single acting, then we've got the condition of a double acting, where there is no clearance, meaning your calculations will be direct. We shall see questions which actually involve a lot of things as we move on, but let us try to revise as much as we can. Also, knowing the relationship that is there between your stroke volume from the diameter and the stroke length. Sometimes, mostly they give you a relationship that is to be taken between the length, which is your stroke length, and the diameter. Mostly you are going to find a relationship, and they'll ask you to calculate the stroke volume. After that, they'll ask you to calculate the diameter. Sometimes they'll ask you to give your answer in millimeters. It's just a conversion that you are making at the end, or sometimes you are to calculate the mass. So it's all about the concept there. The concept is the one that I want you guys to understand. These two, they are equivalent. So instead of being taken from our volume in this case, the formula here, I want you to see something here. Let us consider this part from our formula, because this whole part, if we see here, we are talking about the same formula. This whole part, the n e to n minus 1, this whole part that we see here. All right. And this whole part that we see here are the same. All right. These two are the same. So it simply means also this part that is remaining here, that is multiplying, this part here that is remaining here, that is multiplying, is the same. So it means P1 VE is equivalent to MRT1. So we can even use this formula to calculate the mass in this case. Maybe it's depending with what you're given. If you are given your effective volume in cubic meters per minute, it means you shall obtain the mass in kg per minute in this case. If I am given this in cubic meters per second, let's say I'm given this in cubic meters per second, it means I'm going to obtain the mass in this case in kg per second. So it depends with the question that you are given there. It's going to depend with the question that you are given. But as you can see, it's a relationship that you can consider this one. You're considering P1 with the T1, here having the effective volume. So this is the one that you're supposed to, is it in cubic meters per minute? It determines the mass. Is it gonna be kg per minute or kg per second? If I'm given the effective volume in cubic meters per second, it means the mass there is going to be kilogram per second. So we shall see a question that is directly linking to this formula that I'm explaining. Let's just hope I'm gonna find a question directly to that so that we can take it into consideration as we are revising.